transits, you can do things that change. They're bright, so the atmosphere doesn't need to be perfect, but you can look more nice, or a whole slew of other things that you can do and try and maximize that. And so I believe that's what they were doing. I mean, they're very smart people there. Hypnos and Edvard and all these guys know their stuff. So I think they're going to be trying to target what fits best with the telescope that they have and the amount of time that they have and the location that they're at. But it's really not competitive with even Palomar here. Palomar's near San Diego, so.
I have a question.
Sure.
Is our solar system orbiting around a black hole?
Well, our solar system is orbiting around our galaxy, and there's a black hole at the center of our galaxy.
So we are orbiting.
So effectively, yes, but I mean, there's also all the, like, 50 billion stars which are at the bulge of it, and another, 50 billion spread around. So all of that mass, we see most of that mass, and then there's this dark matter thing. But certainly at the center of our galaxy, you saw the orbits of those stars that were orbiting apparently nothing. There's about a 4 million solar mass black hole at the center of our galaxy. So that gravity we certainly feel, but it's not the dominant one because our galaxy has about 100 billion stars, so 4 million isn't that.
Now, when we're talking about these faraway galaxies, we're talking about billions of light years away, right? So can you say, for example, can you conjecture that some of those galaxies don't even exist now?
Oh, absolutely, absolutely. No, the best time machine on the planet is a telescope. Because what happens is, I'm seeing you a fraction of a second ago, because that's how long it took the light to get from you to me. We see the moon about 3 seconds ago, because that's how long it takes light from the moon to get to us. We see the sun as it was 8 minutes ago. So every ray of sunshine that's hitting you left the sun 8 minutes ago. So the sun could go out, and we wouldn't know for another 8 minutes. We certainly know as we look out at galaxies that are a billion light years away, that is, we're seeing it as it was a billion years ago. And so what's happening now is with that galaxy, this instant, we have no idea. We just know how it looked like a billion years ago. Whether it's gone, it's shifted, it's merged, we don't know. But what we can do is basically a population statistic. What do the guys a billion light years away look like? What do the galaxies 3 billion light years away look like? What do the galaxies 1 million light years away look like? What do the galaxies right around us look like? So what you end up doing is creating a story of the universe based on average, things a billion years ago look like this, then they change and look like this, and then they change and look like what they look like today. So that's what I mean that it's a time machine. You were actually literally looking at things as they were. And we can't say what they are now, but we can say that, well, all the galaxies that look like, there's lots of one kind of galaxy and they're not around today, that means they changed. They became not those galaxies. And so we can actually get evolution in that process just by looking at further and further things.
I'm curious, non-technical question. Were there black holes at the time of the Big Bang?
That's a good question. This was when, it's hard to tell. There's a bit of a chicken and egg kind of thing because we have the cores of galaxies. Every one of these galaxies that has about 100 billion stars on average seems to have a black hole at the center. So if black holes were the seeds of galaxy formation, then they should have started first. So there should have been these big black holes at the beginning of the universe. How would they form though? And we don't know, because if you need it to be the seed, it has to come first. Or there's a process that maybe the galaxies would form or other things would happen, and then things would coalesce, and then there would be black holes, and sort of things would sink to the centers of the galaxy. That's effectively the heavier things would go to the center, and they would form the black hole, or they would make the black hole bigger. Right now, the big question is, how do you form a black hole first, and then get everything around it? So people are modeling this, and they're working on this, because until recently, we only knew of the black holes at the centers of galaxies because of this excess emission of light, the Seyfert-type galaxies or quasars, the idea that material was flowing in, heating up, and we could see it. But that was only about 10% of all galaxies. So everybody was saying, oh, about 10% of all galaxies have black holes at their centers. Then we saw the black hole, or we noticed the black hole, we don't see it, at the center of our galaxy by the influence it has about the stars. And we've started doing that around other galaxies by the influence of the center, even though there's no excess light coming from. And it looks like all of them have black holes at their centers. So now people have just started thinking, it's like, well, we need to see each and every one. How do you do that if you form a black hole at the beginning of the universe, and then how do you do that?
Well, if there weren't any black holes, probably logically, that might be, reasonable to
Oh yeah.
assume. Formation of black holes in the universe have or have not changed the overall environment, or whatever you want to call it. Has the formation of black holes since the Big Bang changed?
Well, our
Or
sense
are
of,
they continuing to change is what I'm leading to.
well,
Are we ultimately going to end up with nothing but black holes?
that's a good question. Probably not, but nothing but black holes, just because, like I said, you need to have, black holes aren't vacuum cleaners. They need to have something, disturb something
Well,
else.
there'll be one black hole.
Yeah.
I mean,
No, I understand, but like I said, you can have things that are orbiting each other perfectly fine for billions of years. Our Earth has been orbiting a very massive object, our sun, for 5.5 billion years. So you may have a lot of things that, you may have some black holes that may become, sufficiently large and sort of collect a lot of stuff around them as they disturb their surroundings. But it's not clear that everything will happen, that everything will, be swallowed by a black hole eventually. Because as it stands, like I said, the black hole at the center of our galaxy, it's not swallowing anything. It's got these stars orbiting it, there's gas there, but nothing seems to be flowing in at all. We don't understand why. I mean, we have ideas of why. They go by very interesting names like advection-dominated accretion flow. But that's a nice set of words, but we really need, that's where we do. We make a theory, and now we need to come up with a way of testing it. And so we're just at that phase. But clearly, black holes can just sit there and do essentially nothing, which is what the black hole at the center of our galaxy seems to be doing. So we're not necessarily in danger of just all being swallowed up by a black hole.
I can sleep tonight.
We'll take one more question.
Somebody that you have to ask.
Well, okay, I'm wondering, they've been crunching WMAP data for quite a long time now.
Yes.
I don't know if they've finished yet, but it's a long process. But I'm wondering what that's telling us about whether the universe is open or closed, whether the universe is going to end in a big crunch or a big freeze. So maybe you can, what the latest thinking is on that.
Just a little review for everybody else. The big question from when the Big Bang Theory came up was what was going to happen. That is, you have this expansion of the universe that begins. If you have enough matter in it, then the gravity should basically stop the expansion and cause a recollapse. But if there isn't enough matter in it, then everything's just going to spread around in just very low density. Or there's what's called the critical density, which is just in between that. Basically, it expands and almost basically stops the expansion. And the microwave background, this sort of heat from the beginning of the Big Bang, has a lot of information in it. And there was a mission that was flown called MAP, which is the Microwave Anisotropy Probe. And then one of the people who was working on it passed away. His name is Wilkinson, and was named Wilkinson Microwave Anisotropy Probe. And my brother and I actually went to the launch because my thesis advisor was actually on that team.
Wow.
So, and they've just done their second release of data. That is, they scan the entire sky, they get all the data, they analyze it, and they put it out there for the community. And then, as the telescope is scanning the skies over again, so they get more data. And I think it's a 4-year map right now. They've put out that. So, but that, along with several other things, has come to the idea that we are in. It's a very strange situation, but it's basically we're in an open universe that will continue to expand forever. But in a strange way, this is where you need dark energies. We're a flat universe, that is. And that's a separate issue to get into. But right now, that's what it is. But that was launched nearly 10 years ago, over 10 years ago now. Just last year, mainly European mission, but with a great deal of participation from JPL itself. That is, we built critical parts of this satellite, is the Planck mission, which is
Fine, yeah.
the same mission as WMAP, except a lot better. And